The title of my talk today, Word Object Learning by Visual Exploration in Space, Wolves, a neural process model of cross-situational word learning. Let me actually, I don't think I did this before, but I acknowledge my collaborators, Ajaz Bahat and Marissa Samuelson. Okay, so words are the building block of language, but a fundamental question is, how do we learn the meanings of words when there are an infinite number of possible reference? So my homey example is, this is my son who's now at university, looks nothing like this. Picture, one of our favorite pictures from when he was a young kid learning language at a very fast pace. So mom says, try some of the banana. And how does he know that banana is this stuff here versus some of the other stuff? And one of the ideas in early word learning is he might track word object co-occurrences across situations. So he might track the fact that banana, when banana is said, there's this white kind of soft substance somewhere in the visual world, and that might contrast with when the word tomato is said or the word cucumber is said. And every time that word banana is said, there's this kind of white mushy stuff. So that must be what banana is. So if we could somehow track the statistics of what's present when words are said, we might be able to figure out word meanings. So there are, a fundamental question is kind of what is the nature of that type of statistical learning? And there are two classes of theories. There are three now, the one I'm going to tell you about, but previously there were two. One is called hypothesis testing and the other is associative learning. So the hypothesis testing view posits that you encounter a novel word and you make a single hypothesis about the word object mapping. Okay, so when I encounter the word banana, if that's a novel word for me, I make a hypothesis that maybe banana maps onto the red stuff, or maybe banana is the plate, right? So it could be any hypothesis, but the idea is I make a single hypothesis, and then if later I encounter a new situation where my hypothesized object isn't present, I know that hypothesis was wrong. So now I might update the hypothesis, okay? So as an example, I might be in an experiment like this, where the experimenter says, oh, look, a zood. And I see that collection of 5 objects, and I might randomly say, well, maybe the zood means the bear, right? And then later I might encounter another array of 5 objects, and I hear, oh, look, a zood, and bear's present. So my hypothesis might be a good one. By contrast, if I look at the first display, I said, oh, look, a zood, and I said, maybe that's the door, right? When I encounter the next display and I hear, oh, look, a zood, I know my hypothesis was wrong, right? So I might update and say, maybe zood means a shoe. And then down the road, I might discover, here's zood again, and the shoe isn't present. So I have to update my hypothesis. So the idea is I make a hypothesis and then I verify it down the road and I update it as needed. So in experiments like this, importantly, I haven't said anything about feedback. Okay, there's no feedback in these types of experiments. Okay, so the idea is you're not learning through explicit feedback and reinforcement learning, for example. You're learning through this statistical cross-situational mechanism, okay? So these are data from the experiment I showed you up above. What you see at the bottom is the proportion correct across blocks of trials. So they're, in this experiment, I believe they learned 12 words across 5 blocks of trials. So in every block of trials, you get each word presented with a visual scene like that. You have to make, you just guess what the word might mean. And over trials, you can see I've got a 1 in 5 chance on every trial of getting it right. So chance is going to be 20%. And you can see people pretty much start out with chance, right? And then over the course of learning, they get above chance. So they actually do learn in this paradigm. Key data for this hypothesis testing view is shown on the right side of the display over here. The idea with the hypothesis testing is if you make a single hypothesis on every trial, if you get it incorrect, you should have no knowledge about what the candidate word might be. because you only tracked one single hypothesis. So if you got it previously incorrect, you should be at chance on the next guess. And that's what you see in the data. Whereas if you got it previously correct, of course, you should be pretty good and you should retain the hypothesis and make the same hypothesis later. So you're quite far above chance on those trials. Okay. So this would be evidence that if I got it incorrect previously, I have maybe no knowledge about what it might be. That contrasts with the associative learning account, which is not so rigid about a single hypothesis on every learning instance. So with associative learning, the idea is that you encounter a novel word and you might form multiple associations between, let's say, many of the candidate objects that are in the array and that word. And then over time, you refine those associations based on the co-occurrences that you see. And of course, this would be a way that you could eventually arrive at the correct word meaning, because the strongest association is always going to be supported by language, right? We rarely say banana when banana isn't present, although we do that, right? So this has been tested in experiments like this. So we might set up an experiment where we have 2 words and 2 pictures on each training trial. Or we might contrast that with an array where we have 3 words and 3 pictures, or 4 words and 4 pictures. And in this particular experiment by and Smith, they taught everybody the same 18 words, but the number of competitor objects and the number of words was varied across conditions. And the idea here is that basically in the 2x2 condition, right, you have fewer erroneous mappings than in the 3x3 condition versus the 4x4 condition, just because of how many words and objects are presented on each trial. And then at test, everyone did the same 4 alternative voice choice test with the same foils. And here's what they found. So basically, they found better learning in the 2x2 condition versus 3x3 versus 4x4. And the idea is that this is difficult to explain from a hypothesis testing view, right? Because the number of essentially distractor items shouldn't matter. If you're forming a single hypothesis, the distractors don't matter. But if you're basing learning on associative learning, obviously the number of distractors matter because the number of associations change. Okay, so those are the kind of 2 existing approaches to cross-situational word learning. In 2012, and Smith wrote a paper in Psych Review and basically pointed out some limitations of these 2 classes of theories. The first limitation is that both types of theories have been used to explain the same data. So that's obviously a bad thing if they can explain the same data instead of contrasting predictions. The second thing they pointed out is that these 2 theories have been applied sort of sporadically in the literature. Rather than explaining data from, let's say, both perspectives, they're often applied to single experiments. So we don't really have comprehensive theories. And then in our recent work, we've also pointed out that these theories have typically been applied to adult data, but there's actually a lot of interesting data on the development of word learning. And so we need to understand how word learning happens across multiple timescales. So one timescale would be the developmental timescale. There's also interesting data suggesting how you learn over the course of, let's say, trials in that experiment, or the experiments that I showed you. Sort of the nature of the learning changes. And interestingly, the nature of the learning changes depending on what you do through real time. And I'll show you that in just a moment. So we've basically got multiple timescales at work here. How you visually explore the array matters, the sequence of learning matters, and the longer timescales of development matter. Let me just give you a flavor of those, a couple of the longer timescales. For example, development. In development, we typically put infants in this particular task where instead of asking them to click on a picture, what do you think the zoot is? We can't do that with infants. Instead, we have to use something like preferential looking to probe what they're learning about. So we might, for example, show them two novel objects like this and say bosa, khaki. And then on the next trial, show them these two objects and say regli, bosa. And then we can probe their learning after many training trials by showing them two objects like this and saying bosa, bosa. And can anybody tell me what the bosa is? The green thing, right? Cross-situational word learning. So in the developmental literature, if we do this type of experiment with 12 to 14-month-olds, some data suggests they can learn 4 words using that procedure. Whereas if we do that with older kids and adults, they can learn 9 to 16 words. So of course, an interesting question is, what's changing over development to enable that better word learning? These procedures have also revealed that how you visually explore the display matters as well. So if we take infants and we classify them as strong versus weak learners, just based on their test performance, data show that strong learners actually have fewer longer fixations during training. Okay, so there's interesting differences in how you visually explore the data that leads to differences in cross-situational word learning. So one of the goals of our project then was to understand some of these nuances about different timescales of learning and how that impacts cross-situational learning. So what I'm going to tell you about now is our model wolves and how that works. I'll then give you a sense for how wolves operates on the timescale of the task, talk a little bit about development if we have time, and then say, is this a good theory? And I wanted to address the issue of, is this a comprehensive theory? And then we can also look at how it compares to competitor models. Wolves is built within the framework of dynamic field theory. And you all know about that here. So on to the next slide. So this is our little box and arrow diagram of what wolves is and sort of what it tries to accomplish. Wolves has an interesting history because it actually is an integration of a couple prior models. And this is a nice theme within dynamic field theory because, one of our goals when developing dynamic field theory was to understand sort of the neural dynamics that operate in one domain, extend those to a different domain, and maybe bridge across domains. And here, what we're bridging across is the domain of visual cognition and the domain of word learning. So in particular, in the schematic, I'm showing you, if I can get my cursor to come up. There we go. Yes. So in the red box here, one of the things we want to capture with wolves is visual exploration in space, how you fixate the different objects and how that visual exploration might constrain word learning. So for example, I just told you about some data suggesting that strong learners have longer, fewer fixations. So how you visually explore seems to constrain what you learn in this paradigm. So we've got a visual exploration in space model, which perceives object features, spatially attends somewhere, does things like working memory and novelty detection, and forms a scene representation of which objects are where in space. And we're going to combine that with a word object learning model that we published across a couple different papers, which basically takes auditory word forms, maps them to visual features, and integrates that with a scene representation. We're going to fuse these two models together to do word object learning via visual exploration in space. Okay. Here's the actual architecture, and this is just a simplified picture, but I'm going to walk you through this through a couple of videos, talk to you about how we perceive features in this model, how we attend to particular objects in the world, like the blue feature on the left, shown up in the visual display at the top here. So the model is currently attending to the blue thing on the left, how that leads to consolidation and working memory. Consolidation then frees up the visual system to fixate somewhere else. We've also got concurrently in this model that it's hearing auditory labels. So we might say regli or bosa. And we then have a way to basically map the auditory word form to visual features. By repeatedly pairing objects, visual objects, with auditory features, the model starts to form associations. But I'll tell you that the model is not simply an associative learner. It's doing some interesting things based on how visual experience structures word learning over time. And we're going to have a memory field here, which is forming memory traces, kind of like an associative learning system. But again, I'll show you ways in which it's not a simple associative learner. Should mention in the full model, I'll show you in the video in the next slide. We're going to take this feature pathway, which is our color feature pathway, and I'm going to duplicate it. So I'm going to have color and shape, okay, to do things like the blue square on the left and contrast that with the red circle on the right. Okay, so here's just a simplified picture of wolves, and I'm going to play a video so you can kind of get a sense for how wolves works. As the video goes, I'll narrate kind of what's going on. So we've got our little smiley face up top that tells you where wolves is looking. So wolves is looking to the orange thing, right? And then it's going to cycle and look to the green thing. When it looks to a particular object, you'll see that object feature, its shape and its color gets highlighted as it attends to that object. As it attends to the object, it's then going to consolidate the item in working memory, which is shown in the kind of middle slices here. Once it consolidates, it releases fixation and it fixates to the other objects. That's why it's kind of dynamically looking back and forth to visual exploration. And what you can see in the last column here is when the words are presented. So there's bosa presented, sends these ridges down into these word feature fields. And basically, whatever visual feature it happens to be attending to at that moment in time, it forms an association between that feature and that auditory word form. Okay, so basically, early in learning, wolves is just going to look back and forth autonomously. It's going to hear these words come in, and it's going to form associations between visual features and that auditory word form. Okay. Now, what I want to do next is break down how wolves operate, and we're going to think about it in the context of 3 dynamic cycles within the model. The first is the visual exploratory cycle. I'll walk you through that, where the model does cycles of novelty detection, consolidation and working memory, and then release from fixation. And that's basically the dynamics that governs how it looks back and forth. Then I'll talk about the word object learning cycle, which is over trials, how the model strengthens associations between word forms and visual objects. And then I'll talk to you about the top-down attention cycle, which is basically how word learning then subsequently influences visual attention. So once you've learned a word representation and that this word goes with these visual features, how top-down attention can then direct attention to those visual features. Okay, so when you hear bosa, I look to the green object, for example. All right, so this first cycle is this visual exploration and space cycle. In each little box in this this figure, you're seeing a schematic of the entire visual cognitive architecture that is wolves. And then across the panels, I'm going to kind of walk you through the details of how visual exploration happens in wolves. Okay, so we're going to start here, present the red triangle on the left and the blue star on the right. You can see I'm showing you, let's say, just the color dimension. I think doesn't really matter. So this is the blue feature on the right here would be this little hotspot, and the red feature on the left would be this little hotspot. And the first thing the model does is it detects that both of these features are novel through this layer we call the contrast layer. The contrast layer, basically what it's contrasting is what's the current contents of working memory and how does it contrast with what I'm seeing in the visual array. And since I have nothing in working memory, as this is the start of a trial, everything is null. So the model is going to then attend to, in this case, the blue object on the right, and the contrast layer here activates the attention layer. This is feature attention here, so it's attending to blue, and this is spatial attention up here, so it's attending to the right side of space. And that just happens initially through noise, okay? If there's no particular salience of one object over the other, we're going to just randomly attend to one of the objects. Once we attend to an object, that sends activation up to this spatial or scene attention level, which is going to be involved in consolidating the features of that object at the scene level in working memory. We'll skip down to the next panel where you see a little working memory peak coming up. This is the working memory for the feature, which again is just that blue feature. And then up here, we've got a spatial pathway, which is working memory for the spatial position, which is the right position. And once those two are bound together at the level of the scene, meaning we know which feature is where in the scene, then we go to the last step, which is going to engage in an inhibition of return field, which basically, once we've consolidated the item in working memory, we're able to release fixation and look at the other object. And that happens through essentially boosting this field. We then activate this peak in the inhibition of return field on the right side, which then suppresses attention at the different layers in the model. And that allows us to now, you can see this little peak emerging for the left side of space. We're now going to then shift attention over to the left. Okay? Yeah.
What determines whether something enters working memory?
It's basically attention determines what enters working. Yeah, exactly. Yep.
Does the local detection work for each independent feature or?
Yes, it works for every sort of feature pathway we have. There'll be novelty detection on each feature pathway, so it'll detect novelty in shape and novelty in color. And you can imagine situations where you might have two similar colors. And so if I am holding pink in my color working memory, red might be less novel than if I'm holding, let's say, very distinctive shapes, for example. So we might have a stronger novelty signal along one feature dimension than along the other.
And if the model has, for example, seen a blue triangle and red star shape beforehand, then it won't recognize the blue star as a new object.
Yeah, so then we get into interesting questions about how long do you hold items in working memory, right? So at some point you might say, like an adult can hold two objects in working memory, right? So at some point, doesn't all the novelty go away, right? So if I've previously consolidated red triangle and I previously consolidated blue star, and both are active in working memory, you could say, does the novelty signal entirely go away? Is that kind of the?
No, I'm talking about the combination, because if you have seen the blue triangle, and then the red star, and then now you see the blue star.
Right.
But when you only look at the color picture, you already have seen that color. And
yes.
If you only look at the shape picture, you have looked at that shape beforehand.
Right. So that's a great question. So there is the important feature basically is that we have bound representations at the level of the scene that are feature space combinations. And so you can distinguish, in the case you were talking about, I could distinguish having previously seen blue triangle or red, let's say red triangle and blue star, and now I'm seeing blue triangle and red star. I can distinguish those.
Yeah. So then he also recognize that.
Yes. Yeah. And that's happening basically through these bound representations in space. Yeah. Good question. Okay, so that sort of describes the visual exploratory cycle. Let me move on to the second cycle, which is the word object learning cycle. So here in the top panel, I'm showing you again the architecture of wolves. What I'm highlighting here is at this moment in time, the model is attending to the red circle on the right. So let's just say red on the right. You can see it's consolidated that feature at the level of the scene representation. We've then passed that feature red into these word feature fields. And at the same moment, the model hears the word bosa. So that passes this ridge down, and at the intersection of bosa and red, we build a little peak of activation. And that's going to leave a memory trace in this memory trace layer. And you really can't see it, but trust me, there's a tiny little light blue square at this position in this memory trace layer. Okay, so initially when Wolves is learning about words, it is literally it's the simultaneous presentation of the auditory word form here with the visual feature coming from the visual cognitive system. It's the intersection of those two forming a peak and leaving a memory trace. And that's basically a very simple form of associative learning. So very early on, it's just doing associative learning. Okay. What I'm showing in the middle panel is now across blocks of trials. You can see how that memory trace builds up. Hello. First one disappeared. There we go. So across blocks of trials, you can hopefully see these little cyan squares, and you can see over the course of 30 trials in this case, it's forming this sort of diagonal pattern, which we built into the model. So that is the correct pattern of word object or word feature associations for what we taught the model. So if it gets the diagonal, it's actually doing a good job. Okay. All right. Now, what I want to highlight is how this feels like simple associative learning. Let me highlight how it's not associative learning. Okay. So what I'm showing you in the bottom panel is how wolves behave late in learning. And at this moment in time, you can see wolves is attending to the red feature. It happens to be on the left in this case, but it's the same feature as above. At this moment in time, I am also presenting the word bosa, just like above. And what you can see is I didn't form a peak in this case. The reason I didn't form a peak in this case is bosa does not mean red. Okay, bosa actually means blue, which you can see in this diagonal representation. So the model correctly learned that bosa maps to the blue thing. And what's happening here in the model is when the model hears bosa, it intersects with this memory trace, which you can see here in the middle panel. That then actually brings up a peak that bosa means blue. And through global competition within this layer, it prevents the model from building a peak at the combination of bosa and red. So the model effectively recalls that bosa means blue, and it prevents itself from forming an erroneous mapping to red late in learning. Obviously, an associative learner would form that association. So because of the kind of nonlinearities of these peak interactions, we get essentially like a blocking behavior late in learning, where it prevents erroneous mappings from forming. Interestingly, you could ask, can the model ever then learn a new mapping? And it actually can. And the way that happens is through essentially decay of that memory trace. So it is open to new learning if let's say you remap what the word bosa means. It could actually learn a new mapping to that word. It would just take some time, and that would happen after the memory trace decays. So we think this is a very interesting property of word learning, and it maps onto empirical data as well, which I could talk about maybe in the discussion period. Okay, I'm gonna, in the spirit of showing you more than just how the model works, I'm gonna kind of skip over this last bit. And I'm just going to say, trust me that once you've learned a word representation in wolves, when you recall what that word means, that can influence top-down attention. And the way that happens is through connectivity between the word feature representation I just showed you and projection onto the contrast layer or the novelty detector in the model. So the way we think about top-down attention is when you hear a word and you recall the features of that word, that primes those features to be novel in context, meaning you're going to search for those features in the visual array. So if I remember that Bochum means the blue thing, I'm going to then prime the model to look for the blue thing when I get the Bochum input. Okay, so let's go on to asking the question, does wolves capture and explain empirical data? And as I do, I'm going to show you return to the hypothesis testing and associative learning accounts earlier, the data I showed you previously, show you that wolves actually captures those data. And I'm going to contrast that with an associative learning account from Kacherkis. In their model, they have a model that basically distributes attention between known and novel associations. There's some memory decay in their model. Importantly, from my perspective, their model is kind of one shot on each trial. It doesn't actually unpack what happens on a trial. So there's no visual exploration in their model and things like that. And I'll come back to that in a couple of minutes, because that allows us to explain things like why fewer, longer fixations provide better learning in a cross-situational word learning. If you do one-shot computation on every trial, you can't unpack what happens during the trial, right? Okay, so here's the data I showed you previously from this paradigm where you had the 5 objects and we said, oh, look, the Zood. Okay, what you're looking at on the left is that learning rate. The actual data I showed you before are in blue. The performance of wolves is in red. You can see we pretty much perfectly modeled the data. The Kacherkis model, which is the associative learning model, doesn't fit the data particularly well here. That's important. This is sort of considered a canonical hypothesis testing experiment. So it's been used to argue against associative learning. And you can see why, because an associative learning model doesn't capture the data terribly well. In particular, the associative learner has real trouble with this incorrect bar. So if you were previously incorrect on a trial, the associative learner has stored something about that trial previously, and it does better than people do. Okay. Now you can see Wolves does a really nice job of capturing the data from this hypothesis testing experiment. And of course, the interesting question is why? Because you might think wolves might actually might behave a little bit like an associative learning account. And the reason wolves captures these data so well is because of an interesting property of what participants do in the experiment. In the experiment, without any instruction, participants respond very quickly, probably because these are undergraduates in the United States and they just want to be through the experiment. And so when they hear BOSA, they basically make one fixation, they click on the object, and they move on to the next trial. So participants spontaneously moved through the trials very quickly and only made one fixation. If wolves only makes one fixation, it only forms one association on every trial, and it behaves kind of like a hypothesis testing model. Okay, because it basically, yeah, does that make, hopefully that makes sense, right? You basically look at the bear or you look at the door, you say maybe Zood means door, and then you move on. And you don't really encode much about the other objects. So that led us to say, well, how would wolves behave if we forced it to basically make lots of fixations? Okay, and so this is how wolves behaves when we ask it to make multiple fixations and we kind of slow the model down a little bit. So what you can see is that early in learning, wolves shows that hypothesis testing signature. when it gets it wrong, right, it's actually at chance on the next trial. But over the course of blocks, you can see if we force wolves to make multiple fixations on every trial, it starts to creep up above chance, right? And after multiple blocks of training, wolves is now showing better than chance performance, right? Even when it got it incorrect on the previous trial. Interestingly, you also see an increase in performance on the correct trials as well, right? So that's just happening as the association is getting stronger and stronger and stronger. So we tested this experimentally. We put college students in this task, and we basically said, you can't respond until you hear a tone. So we forced them to sit there for 6 seconds, study the array, and then click on what you think the zood is. And here are the data from that experiment. And you can see after several blocks of trials, undergraduates were above chance on the incorrect trials, just like the model. And you see this nice increase in performance on the correct trials as well. Okay, so that's just an example of generating a novel prediction from our model, which survives an empirical test. Wolves also does a nice job of explaining data from this canonical associative learning experiment where we had that 2x2 versus 3x3 by 4x4 experiment I described earlier. You could see the data I showed you previously in yellow from you and Smith. Wolves fits the data nicely in the blue bars. Associative learning account explain these data just fine. Fit of the model isn't great again, but pretty good. Of course, since we have a model, we can ask why participants showed poor performance in the 4x4 condition. And you can see it's exactly what you probably think from an associative learning account. So across conditions, the number of incorrect association wolves forms goes up, right? With more distractors, it's forming more erroneous associations. The association strengths are going down because there's more distractors, more things to associate, just like you might expect. Yeah, so wolves provides a nice account of these canonical associative learning data as well. Okay. In just the last couple of minutes, let me return to that issue of unpacking why fixation matters to learning early in development. First, let me show you that the model does a nice job capturing early developmental data. So we could take the same model and put it in that preferential looking paradigm, right, and ask, does it capture infant's behavior? We, of course, have to tune it to be an infant model. We do that by essentially slowing down learning. Okay, so our infant model, the big thing that we ended up changing in this model is the decay rate on the memory trace. Okay, so in the infant model has fast forgetting, and the adult model has very slow forgetting. Okay, so that means kind of the model learns slower. And you could see in terms of looking behavior, the model does a nice job of capturing infants' performance. So infants tend to look at the target more than the distractor. So when you say BOSA, right, they get their eyes to the BOSA and have longer looking to the BOSA, suggesting that they learned what BOSA means. Wolves mimics that performance pretty well. But we were particularly interested in the fixation data. Like, why is it the case that infants that learn better show fewer longer fixations? Okay. Here's just a table from showing you the infant data, mean fixations per trial for actual infants. And you can see the strong learning infants have fewer fixations with a longer fixation duration. Weak learning infants have more fixations with a shorter fixation duration. This is kind of counterintuitive in the developmental literature because we typically think infants that show more fixations with a shorter duration are fast learners. Okay, So you could say, why are the fast learning infants actually learning less in the experiment? So there's a kind of tension in the literature that the way we think about fixation dynamics with infants doesn't seem to fit the learning that we see in this paradigm. So it was interesting to ask, could wolves explain this kind of counterintuitive finding? And so what we did is basically manipulated in wolves a parameter that influences the number of fixations, which is how strong the kind of spatial pathway is. And I can explain that in a little bit later if you like. But basically what we see is if we sort the models based on how they learned, strong learning models here overtraining show fewer fixations than the weak learning models in blue. So the axis here is number of fixations per looks. And if we go into what's going on with the learning in wolves, what you can see is that as the fixation count goes up, the strength of the word feature associations goes down. And as the fixation count goes up, the number of erroneous fixations goes up. So basically what's going on in wolves is when it is generating lots of fixations, it's forming lots of erroneous associations. And that simply happens because you're more likely to be looking at the wrong thing when the word comes in and form an erroneous association. Okay, so it makes perfect sense, but it didn't make perfect sense until we had a model to explain the data. So that's, I think, a nice case where once you understand kind of the mechanisms of how visual exploration and essentially associative learning is working in this paradigm, it reveals new properties of the data or nuances of the data. Okay, I'm going to just skip through our developmental story, which I was expecting to have to skip anyway. Let me just end by this simple question of, is wolves a good theory? So we ended up comparing wolves to two competitor models, essentially the best associative learning model out there and the best hypothesis testing learning model out there. And we, you could see, fit the data from 5 cross-situational word learning studies with adults and 7 cross-situational word learning studies with infants, toddlers, and children. And the summary of the performance is down below. So you've got wolves. This is the associative learning model, and this is the hypothesis testing model called Pursuit. I'm showing you the root mean squared error across fitting the data from these 12 experiments. There's 69 data points ultimately we could fit. And if you look at the root mean squared error column, get my cursor back. I don't know why it keeps disappearing. There you go. You can see nice low root mean squared errors here relative to the other 2 models. Importantly, when we did the fitting, we fixed the parameters of all the models and then asked, could the parameters generalize to new experiments that we didn't explicitly fit? That was an interesting exercise, and you could see wolves actually does a really nice job fitting data from these new experiments. The other models actually do much worse when generalizing to new experiments, which we thought was interesting. So it seems like wolves has good power to generalize to new paradigms. And then importantly, we were able to fit data that the other models couldn't fit, right? And the reason is simple. We have a visual exploration model. So these new data points that the other models can't explain comes from the fact that we have visual exploration, so we can fit fixation rates and mean look durations and things like that. The other models are all one shot, so they have no way to essentially go into those types of data. So everything I've shown you in the middle blue bars suggests wolves is a fantastic comprehensive theory. The last bar, though, is really quite fascinating too, because then we need to say, what's the canonical measure you usually use in the literature to compare models? And it's something like the Ake-Ike information criteria, which penalizes models for the number of parameters. Okay, if you look at that, with the AIC measure, low values are better. So you could see the Kishirgis model is the clear winner here. Okay, so it's a clear winner in terms of the canonical criteria people use to compare models. The reason it's better is it's got 3 parameters, and Wolves has something like 72 parameters we counted up. Okay, but I've shown you in this talk that the Kishirgis model is a terrible fit to those hypothesis testing data, right? I've shown you that it doesn't generalize terribly well, but by this metric, it's the winning model. So that, to me, suggests we need to think a little bit more about how we evaluate models quantitatively, and especially when we do that with neural models versus non-neural models, because of course the number of parameters is always going to be bigger in a neural model. Okay, so I've told you about our model, highlight a little bit about how it does some of the different timescales, emphasize at the end that it's a comprehensive theory, and we're continuing to work with this model, trying to generate new predictions and things like that. But let me end there by thanking my collaborators, funding, and take any questions that you have.